Right. So in terms of content, as I said, we will in the first part of the course we will focus on salient pole synchronous machine, and we'll look at the two-axis theory of synchronous machines, which we haven't touched at all in Machines 2. Then we'll look at the principles of electromechanical energy conversion, and that will be basically looking at, as I said, the modeling of the synchronous machine using basic principle to derive the equation to represent the synchronous machine. And we'll move on to the next section, which is on generalized machine theory and primitive machine. So these two sections are the ones that will present the equations for the primitive machine in matrix form, and then we will demonstrate how can this this generalized machine theory can be applied to, for example, demonstrate the DC machine that you've studied in the previous modules. We can basically use them to demonstrate how these machines can be basically represented mathematically. And then we will also analyze some of those machines during the tutorial. Right, and in the next section, we will look at, as I said, transient behavior of synchronous machine and DC machines. So again, we will look at mathematical models on how to model the transient that happens in synchronous machines as well as in DC machines. All right, so once we finished this, the very last section, we will represent this closed loop control of DC machines. Okay, so in this course, we will have basically, in terms of assessment, we will have 3 tests, right? And you will have 1 practical assignment. And the 3 tests, for now, we've planned it to be online, right? So so the weights are distributed as follows. So you will have 3 tests, each carrying 25% of the course mark, and the practical assignment will carry another 25%. Okay. So just I've basically highlighted this in red. Just be very careful when you're writing your test online. There won't be, I will not accept any late submission via email. So only your PDF scripts that are uploaded via Moodle will be marked. So just take note of that. Now, in terms of assessment criteria, so the test will be basically designed to test your understanding on the material of the module. So for each section, we will basically design the test question to test your understanding of the concept of, for example, salient pole machine. And then you will have to apply this knowledge to analyze the machine in different, for example, application. And there will be also the practical assignment that will be given. So here we will look at how you can use the software to basically represent some of the sections of the course that we will deal theoretically, and then you will basically now use a certain software. In this, actually, I've prescribed PSCAD in this section, so you will use PSCAD to basically simulate the transient response of a synchronous machine, and I will basically give you a certain specification, and then you'll have to basically do the practical assignment and demonstrate the result of the transient response. Right. So again, this will be assessed by a practical assignment. Again, it will be online, where you'll have to submit your report via Moodle for the practical assignment. So in terms of learning and teaching and learning approach, we will meet via Moodle, basically as per this arrangement. So we will meet on Mondays between this time, 12:20 to 1:05. That's for your Monday session. And so the lectures basically will be given to provide you with concepts and methods. And obviously, we have replaced the practical for now with a practical assignment for now, because we're not running practicals during this current period. So once you've basically done your lectures and practical assignment, also your tutorials will basically help with enhancing and test your understanding with the different basic concepts, right? So normally the lectures I will basically conduct them on Monday and Friday, and there'll be an additional session for tutorial on Fridays. But I will basically inform you in advance. Just remember, for an 8-credit module, so you normally have 2 45-minute lecture per week, and the tutorial is normally alternate. So 1 week you will have tutorial, and the other week there is no tutorial. So the loading is alternate for the tutorial session. But if, for example, there is a test coming, or then I will, or we're lagging behind with the course, then I will use that additional lecture session or tutorial session for just making sure that we meet our target and prepare you guys for your test. Right, so the tutorial will be posted on the learning website, and the assignment on machine transients will also be given via Moodle, and it will require the use of PSCAD. Okay, in terms of the notes, they are based on those textbooks, but I will provide you notes for all the different sections. So these textbooks have just been presented just for your reference only. You don't need to go and purchase those textbooks, because my notes have already basically covered all these different textbooks that I will provide. All right, so I will now just get you introduced with the first part of the Salient pole machine. So this is the introductory part for the first section, which is Salient pole synchronous machine. And when we basically covered the first course on Machines 2, we focused our analysis on this first part, which is what we call cylindrical rotor, right? So if we focus on this diagram, I'm just going to zoom in here. So if you look at this figure, part B here, this is an example of a cylindrical rotor. As you can see, these slots are all uniform around the rotor, and that's your stator slots. And when we've analyzed cylindrical rotors in Machines 2, we've modeled the synchronous generator with just one reactance, which is called a synchronous reactance, right? So this synchronous reactance is basically representing the armature reaction right? So due to the flux that's produced by the rotor pole and passing through the air gap and going through the stator iron and coming back. So it's modeling, if you look in the next figure here, this is an example of a cylindrical rotor where you have uniform air gaps in the machine, and it's producing a very uniform flux, right? So as you can see, it's a 4-pole machine, and each pole is producing its flux going into from the rotor to the stator, from the north to the south end of the adjacent pole, and the flux phi2 is uniformly distributed along the air gap. Okay, so because of this uniform distribution of the flux along the air gap, the machine equation is very simple. We can just if we look at just going to zoom out. So the armature reaction that's used to represent reactance. So the reactance, as I said, which is XS that we've used before. That was very easy in the first case because as I said, the cylindrical rotor has what we call uniform air gaps from what we've seen here. It has uniform air gaps, right? So now if we go to figure A, this is an example of a salient pole rotor. Okay, so the salient pole rotor, as you can see, it's got a different structure where you have a certain axis where you will have the length of the air gap is different to that if you look in this is called an interpole region, right? So between the region between two adjacent poles, this is a 4-pole salient rotor machine, and this area that lies in between the pole is called the interpole area. And as you can see, because you have this interpole area, now the distribution of the air gap is different along the axis of the pole and in the axis of the interpole area. Okay, so obviously then the salient pole machine, it has what we call non-uniform air gaps, right? Because of the interpole region, right? So because of this non-uniform air gap, as you can see in figure A, we've basically divided the machine into two different axes, right? So you have an axis that's along the pole of the machine, okay? And we call that the D-axis. And we have one axis that's basically along the interpole area, and we call it the Q-axis, okay? So these two axes is what we refer to as two-axis theory in this salient pole analysis. Right. So as I was discussing earlier, I said because now you have what we call cylindrical rotor has uniform air gaps and salient pole have non-uniform air gaps. So the armature reactance that is used to represent the armature reaction flux in a cylindrical rotor machine cannot be used to represent the armature reaction flux in a salient pole machine, okay? Because their structure is different. Obviously, the flux distribution in the air gap is different for a cylindrical rotor and a salient pole rotor, okay? So if we move to the next slide, you will see that I've also now shown you how the flux is getting distributed in the air gap. So we've zoomed in more in the cylindrical rotor first, right? So when we had cylindrical rotor, so that was what we analyzed in machines 2. We had, you can see there, the slots on your rotor is producing the flux that's passing onto the stator. And we found that for cylindrical rotors, same armature reaction MMF produces same flux irrespective of the rotor position because of uniform air gap. So basically, as the rotor moves along the stator with respect to the stator axis, so it's telling you that um, the same MMF reaction, the same armature reaction MMF. So remember, your MMF is the number of turns, right, times the current on the coil, and that is producing the same flux in the air gap, irrespective of the rotor position. Okay, so in this particular configuration, your synchronous reactance, which we were using in the equivalent circuit, is representing two components: your armature reaction and the leakage flux. Right, so that's for your cylindrical pole rotor. Now, if we slide down to what we call the salient pole rotor, you'll find that if you look at the flux distribution in the machine, you will find that in the pole that's along the d-axis, so the axis of the pole, we'll find that because the what we call the reluctance is different as compared to the reluctance in the air gap in the interpole area. Obviously, if the air gap is larger, you will have more reluctance and obviously less flux passing in this axis as compared to an axis where you have less reluctance. Obviously, then you have more flux passing in this axis. Right, so now because now you have two different reluctance, obviously, the magnetic reluctance along the poles is low, and it will be high along the interpole area. Okay, so obviously now we cannot use only one synchronous, armature reaction now. We have to have two of them because there is two different axes where the reluctance is different. Obviously then the flux distribution is different. So now, as you can see, we've splitted the reactance into two different components. You have what we call XD, so that will be your D-axis reactance, and XQ will be the Q-axis reactance, right? So that's the axis along your interpole area. And so for a particular armature reaction, the MMF will produce more flux along the D-axis, which is your pole axis, and it will produce less flux if it is acting along the interpole axis, which is your Q-axis. So now, instead of having one component, you will have two components, right? And obviously, the D-axis and the Q-axis values are different because your reluctance is different. Okay, so XAD and XAQ will be different, right? And also the leakage reactance will be different in each case. All right, so if we move to the next slide, here basically we're showing how, so F is your flux, the MMF along AD, and that's the MMF. FAQ will be the MMF along the Q axis, right? So the flux density due to the D-axis MMF is shown here as the dotted line, okay? And the flux density due to the MMF along the Q axis, which is BAQ, is shown here in the dotted line. as you can see, the frequency of your q-axis flux density is different from that of the d-axis, right? So here the d-axis is giving you the same frequency with the MMF of the d-axis, and here, as you can see, it's doing two cycle within one cycle of the MMF of the q-axis. So it's telling you that the frequency is like twice that of the q-axis MMF. So when we model the equation, you will see that when we adding that component due to the q-axis, you will find that there is a difference in the frequency. Okay, that will reflect onto the reactance of the machine, right? So now, when you're looking at cylindrical rotor, so you will have basically the q-axis being equal to the d-axis, right? So then you end up with just one curve, sinusoidal curve, and then you can say xs is xd because now it's a cylindrical rotor and it's uniformly distributed and it's sinusoidal. Okay, so this is what you have worked on before, but now you will be basically working with a more complex case where you will have two components, right? You have your d-axis and your q-axis. Right, so this is just a revision of your basic magnetic equations that you can look at, how your flux is related to the reluctance and the MMF, and how your reluctance relates to the length and the cross-sectional area of the magnetic circuit, right? And also how the induced voltage is basically related to your magnetic flux using Faraday's law. So basic revision here of your Faraday's law, how the flux basically is leading the EMF. So there's a 90-degree shift because you have E is equal to d phi by dt there. So obviously then you're getting a 90-degree shift between the two sinusoidal waveform, right? So when we are gonna look at the q-axis and the reactance and the d-axis reactance, just take note that the armature reaction in the d-axis is given by this formula, okay? And it's showing you that the d-axis reactance, right, can be, when you designing the machine, the factors that may influence your d-axis reactance and q-axis reactance is L, G, D, right? So that's the length of the air gap along the d-axis and the length of air gap along the q-axis. So since when you look at the figure 1, you saw that the d-axis length of air gap is much less than the q-axis, obviously. So that translates to the reactance on the d-axis being higher than that of the q-axis, right? In terms of reactance, right? So in the design, if, for example, you're designing a salient pole machine, if you want to vary XD and XQ, what you have to do is LGD or an LGQ are the two values that you need to vary in your design to vary those two reactances. Okay, so the physical parameters will translate into your electrical parameter that is appearing on your equivalent circuit. Right, so as I said, now if you're working with a salient pole machine, as the waveform of your current is basically sweeping across on the rotor side, and getting, so we will look at three cases. when your phasor, your current phasor, so that's your current in the stator, is acting along each of those axes, we will show how the sinusoidal current is looking at between, the sinusoidal flux of the field winding and the armature is basically distributed along the basically the air gap. So this is your rotor side and this is the stator side, and they are producing two waveforms. One is the field flux and one is the armature reaction. And so when the current is acting along the Q axis, right, so this axis, Q axis there, remember that the D axis will have its flux, and the armature, which is your stator side, will have its own flux due to the current that's induced on the stator side. Now this reactance, which is your Q-axis reactance, is given by the ratio of E AQ over AI AQ, right? And remember that the induced voltage is proportional to the flux, right? So when the current is acting along the Q axis, this is how the two fluxes are. This is how the two fluxes are basically positioned along the air gap. And when your current is acting along the D axis, right? So that's your stator current is acting along the D axis. So this is how the flux distribution looks like. So you can see that the field of flux is out of phase completely with the armature reaction flux, right? So here in this case, they're acting against each other there. One is pointing upward and one is downward. This is your phasor, and here is your time domain. So here you find that, again, your x AD will be given by E AD over I. And obviously, as I said, we looked at before, your reactance of the D axis is greater than that of the Q axis. So, and again, if the current is acting in between the D and Q axis, you will have basically three waveforms, your FD, FQ, and your armature reaction. And this is how it looks like now. You'll have IA in between the two axes, and now you will have the current that is split. So we're resolving the current into two components. You'll have ID and IQ, and this is what we're going to look at in our phasor diagram, how ID and IQ produces two different reactances, which is XQ and XD on each axis, and how they are represented on the phasor diagram. Right, so I will just introduce this first equivalent circuit, which is slightly different from what you've studied in Machines 2. So if you remember, in Machines 2, we just had one reactance, right? So we had your induced voltage, one reactance, and your stator resistance, and that's your terminal voltage for the generator. Now, when we work with the Salient pole machine, as you can see, what we've done is we've splitted these reactants into two components. So you'll have the D-axis armature reactance, and so armature reactance and the Q-axis armature reactance. So those two reactances will produce two components, right? So you'll have ID and IQ, right? And again, we will basically apply the same principle to draw the phasor diagram where the sum of the voltage at the terminal plus the drop across the resistance and the two components there will give the induced voltage as shown here. Okay, so as you can see, we will take our terminal voltage as the reference. Okay, same like we've done in the cylindrical rotor. Then your drop across the resistance of the stator is in phase with the current, same as in last year's course. So then basically now the phasor that used to be here between this phasor and this phasor now is split into two components. Instead of having one here, we split it into two. You'll have ID XD and IQ XQ, and that will give you your induced voltage, right? So now the how we get those two phasors is from this, we resolve this current here, right? So we will resolve the current I. So IQ will act along the induced voltage, and ID is perpendicular to IQ. Okay, so when you're drawing the these phasors now, you will find that IDXQ will be parallel to this phasor, which is the induced voltage, right? And remember that the reason why it's parallel to this is because when you multiply XD to ID, it rotates the phasor by 90 degrees, okay, due to the reactance of the inductor. The drop will be 90 degrees shifted. So obviously, if ID is pointing here, 90 degree to that will be along E node. So obviously, then this is along E node. So again here, as you can see, IQ is acting along E node, and obviously the drop due to the current, when you multiply by the reactance XQ, it will be 90 degrees with respect to the current IQ. So now it's pointing 90. So obviously you get a 90 degree shift from IDXD to get IQXQ. All right, so this is the equation that represents this phasor diagram. And if we neglect the reactance of the stator or armature, what we call it, then you end up with just a simpler equation where E is equal to, E naught is E plus IDJ XD. This is the J operator, as I'm explaining, is rotating your phasor by 90 degrees. Again, here you have IQ, JXQ. Again, it's this phasor here. Okay. All right, so I will stop here for today, and I will post the notes on the Moodle website for you to go through it. And so Friday when we meet, we will just continue with the lecture. So before I end the lecture, I'd like you to, if you have any question, please unmute yourself.